Alright, so as promised in the last video, what was the equation actually determined for gravitation? And it's not really the F equals mg that you've learned about, although it is related to that. And we actually do find a new form of F equals mg that continues to work even with our new formulation for gravitation. So here it is. The new form for gravitation is going to be F is equal to some constant, big G, mass of the first object, mass of the second object, divided by their distance squared. Now this is just giving the magnitude. So let's think about how this works. We have a couple objects. Let's make a big one, object 1, and then let's make a smaller one that we'll call our object 2. Based on the distances between their centers r and the masses of each of these two objects, we can figure out what the force between the two objects will be. So m1 and m2 are masses in kilograms. Let's see, r is the center to center separation, and that would be in meters. Let's see, big G. Big G is the fun one, gravitational constant. It is 6.674 times 10 to the minus 11, and the units on this can get kind of interesting. Depends on how you want to think about them. Newton meter squared per kilogram squared would work perfectly well. We believe that big G is the same everywhere in the known universe. Maybe it is, maybe it's not. It's hard to tell just by looking at distant galaxies. We also believe that it doesn't change over time, although I'll warn you, every time we've made the assumption the universe is static, we've managed to be wrong so far. So there's a chance it actually does vary based on where you are and when you are. But for the moment, we think it's a constant that doesn't change and is just a property of the universe. All right, F is the force, and it is measured in newtons. Some things to notice about this. What happens if you double one of the masses? So if you double the mass, you'll double the force. If you double both the masses, well, now it'd be 4 times the force. But here's the interesting part. Doubling the distance gives you 1/4 of the force, and halving distance gives you 4 times the force. So it turns out gravitation is very sensitive to distance and not as sensitive to the mass. It's just proportional to mass, but it's inversely proportional to the square of the distance. So it falls off relatively rapidly with distance, but I'll point something else about this equation. It's over r squared. Where would this equation go to 0 if we keep increasing the distance? And of course, the answer to that is effectively infinity. We'd have to go really far away before gravitation would fall to 0. So maybe we could also think of it as universal because it spreads throughout the entire universe. Alternatively on this, there's something weird that happens if you let the distance go to 0. Fortunately, things collide with each other before they'd be on top of each other. But it's interesting to notice that this has a discontinuity at 0. And it's actually one of the reasons why gravitation is proving problematic for quantum mechanics to deal with. Now, what gravitation actually is the curvature of space-time caused by the presence of matter. And this model of gravitation we're talking about right now doesn't get into that. General relativity is the proper model for gravitation at this moment in time. It's our best model of gravity. It has replaced Newtonian gravitation, which is what we're learning. You might be thinking, why are we learning it then? Well, this is mathematically a lot easier. So we're going to use it, and we'll learn about it, and based on it, we'll do maybe cool things in the future. All right, some more things about this force. It is a vector force, and the way it's written as a vector is probably going to make you feel a little uncomfortable, because one of the ways of writing it uses the vector r hat. r hat is a unit vector. And it has a length of 1, and it points from the center of your coordinate system to somewhere else. Now in this context, when we're using it, we pretty much inevitably put our coordinate system, whoops, wrong tool, put our coordinate system at the center of our more massive object, and then we set our less massive object somewhere else. And now we can actually show what r hat would be. R hat will be a vector with a length of 1 that points directly from the center of the coordinate system to the center of our mass 2. Okay. And whoops, forgot one thing. So this would be the force due to mass 1 acting on mass 2, and notice it's acting in the negative r hat. It's acting back in this direction. Because it's acting back along the r hat direction, that's the reason why the minus sign is typically shown inside of the gravitation formula. Come to think of it, in my previous one, I really should have put a minus sign here, but we were just talking about magnitude, so we're okay. All right. So minus r hat indicates the direction. And if there is, in fact, a force, F12, that tells us about the force due to 1 acting on 2, you'd better believe Newton's third law is telling us there's another force with exactly the same magnitude called F12, called F21, my bad, that acts from mass 2 on mass 1. So this would be the force due to 2 on 1. They are a third law pair, which means if we consider the system to be both objects, they will cancel out. And if we're writing the form of F21, it would look like plus gm1 m2 over r squared, r hat, using our current coordinate system. Now the whole minus and r hat thing, that's all about coordinate systems. I do have a little link at the bottom if you're interested in reviewing things like vectors and r hat or unit vectors. So be sure to watch those if you're feeling uncomfortable with them. We do talk about them in 1A, but we don't use them a huge amount. To be fair, we're still not going to use them a huge amount, but direction is important to think about, and forces are vectors. So they have both a magnitude and a direction to get a proper answer. Okay. The last thing we're going to talk about for the moment is how is this gravitational force determined? And it uses something called the Cavendish apparatus. Now, what is that? Well, functionally, it is a wire with a little bar hanging on the end that has a couple little masses on it. So it looks like a barbell, a dumbbell, something you'd lift in the gym. Then what they did is they brought much larger masses near this on either side. So small masses on the apparatus, large masses here. They could figure out the distance center to center. They could figure out r. And what happens is this bar twists slightly under the influence of the gravitational force of these two masses. And what you do is you get a little mirror and you put it on the thread, so as the thread gets twisted, you can shine a beam of light on it and reflect it a large distance across an entire room. That takes a really tiny angle and turns it into a larger distance where you can actually measure it and determine the angle of deflection. Then what you would do is take the same fiber and put the masses in the opposite location at the same distance. And now the trick of this is, oops, forgot to change tool again. You get your r distance with your masses, big M's and little m's, and this causes the fiber to twist the other direction. So based on twisting the fiber, you can figure out what the angle of twist is based on the twist. There's another formula for torque that would look like, let me see, what does it end up looking like? Kappa times theta. It's not one you would have learned about in your previous class, but this is the torque equivalent of a simple spring. And this is actually the reason why Hooke was involved in all of this. Like Hooke and springs kind of go together, and Cavendish and Hooke and Newton all talking to each other was a thing. All right, so based on the angle, you can figure out the torque. Based on the distance to the masses, you can figure out the torque going along the lines of r cross F. Technically 2 times r cross F in this case. And you can set those effectively equal to each other. Now, you have to know the stiffness of the fiber. You have to know kappa. But it turns out you can figure that out by applying very small loads that you know the size of to twist the fiber around. So you can characterize it just like you'd characterize a spring. And knowing that, you can set these equal to each other, and you can determine F. And now you can play with it. You can start changing the size of some of the masses, for instance, or you can change the center-to-center distances. And you can carefully peel out from all of that there's a direct dependence on the mass and an inverse squared dependence on the distance. Now, interestingly, the original Cavendish apparatus wasn't used to determine big G. That came some years later. But the Cavendish apparatus is still in use today, measuring big G to ever higher and higher precisions. Knew a guy, he was a professor emeritus when I was at UC Irvine. He gave a very interesting talk about his entire career, which was basically measuring big G to higher and higher precisions, and also looking for new physics. So you may not be aware of this based on your 1A class, but gravitational mass and inertial mass, the mass you see in F equals ma, they aren't necessarily the same thing. There's nothing in the theory that says they must be the same thing. We've observed that they always are the same thing. But because they don't have to be, some of the experiments that this guy had been doing in his career were looking for, is there any weird exotic material we can use that doesn't have the same gravitational mass as its inertial mass? And that would lead to new physics, because like I say, it's not really part of the theory. So, kind of cool stuff. What's most important for us here are the equations, particularly the one with the vector form here. We're going to try a couple of practice problems related to them, and they will be in their own videos coming up next.